Chapter 9 is devoted to what are called sequences and series. Briefly, a sequence is an infinite list of numbers, and a series is the sum of an infinite list of numbers. We start today with a discussion of sequences. We define a sequence as a list of numbers, and we introduce some of the notation associated with sequences. We often use curly brackets around some S sub n to indicate some formula that'll generate the sequence depending on the value of n. To indicate that it's just a list of numbers, we have commas in between S1, S2, S3, and so on, with the 3 dots indicating all terms in between S3 and Sn, and then the 3 dots after the Sn, indicating that the process continues forever. So as our first example, S sub n could be the quantity 1 over n. To write down the sequence, we need to plug in values of n. So the first term in the sequence would be 1 over 1. And then if n was 2, the second term in the sequence would give us 1 over 2, or 1/2. Then we would have 1/3, or 1 over 3, 1 over 4, 1 over 5. And then we can't get them all because it's an infinite process, so the list would continue. Next up, we have the sequence generated by n squared. So this would look like 1 squared, or just 1, 2 squared, which is 4, 3 squared, which is 9, 4 squared, or 16, 5 squared, or 25, and then we indicate that the list would continue with our 3 dots. This next sequence is one that's often used to generate signs changing from positive to negative. So this will come up a lot in the work that follows. But the idea is if we take minus 1 to the first power, we would just get minus 1, and then minus 1 to the second power, minus 1 squared, or positive 1, minus 1 cubed, minus 1 to the fourth, minus 1 to the fifth, and so on. And then this is more commonly written in its simplified form. Minus 1 to the first is negative 1, minus 1 squared is 1, minus 1 cubed is negative 1. So all of the even exponents end up giving us a plus 1. All of the odd exponents end up giving us a negative 1. Our final example is just another formula where we have to plug in values of n to generate the sequence. If I plug in n equals 1, I get 1 minus 1, which is 0 over 1. I could just write 0 for that one. If n was 2, I would get 1 minus 2, or negative 1 on top, over 2. If n were 3, I would get 1 minus 3, which is negative 2 over 3. And then the pattern would be minus 3/4, minus 4/5, and so on. There are a couple of different ways that we can represent a sequence graphically. One is to use the xy plane, where our x-coordinate will be n, and our y-coordinate will be the value of the sequence. So we'll use the sequence that generates alternating signs on top, minus 1 to the n, with positive integer denominators. So our first term would be minus 1, the second term would be a half, third term minus a third. Then all even denominators would have positive signs, and all odd denominators would have negative signs. Now the following animation will show what the graph of such a sequence would look like. So it's going to plot it over and over again. The first term here would have x coordinate 1, y coordinate minus 1. The second term of the sequence would be found here with x coordinate 2 for n equals 2 and y coordinate equal to a half. The next term in the sequence would have x coordinate 3 and y coordinate minus a third. Then we would go to the fourth term in the sequence, n equals 4, y equals 1/4, which we can see here. It's about 0.25. And then we just plot the rest of the terms. You can see they're alternating sign between plus and minus because they're either over the x-axis for plus or below the x-axis for minus. The dots are getting closer and closer to the x-axis. They're approaching 0. Now we can also represent sequences visually on a number line instead of the xy plane. We'll use the same sequence as before so we can contrast the different visualizations. So once again, we'll have an animation that's going to plot the sequence over and over again, and it'll rerun and we can talk about it as it does. So on this animation, notice that the very first term is here. This is my n equals 1 term, that's minus 1. The second term would be here, my n equals 2 term, or a half. And then the third term would be my minus 1/3. And then the fourth term would be the fourth. And the fifth term would be minus a fifth. And then we'll continue bouncing around 0. We would have a sixth minus a seventh, an eighth minus a ninth, a 10th minus an 11th, and so on. The fact that they're alternating to the right and left of 0 tells us that the sign is changing from plus to minus. And the fact that they're getting closer and closer to 0 is shown in the fact that the denominators are growing without bound. So the animation, of course, can't plot all of the terms in the sequence. It plots the first 20 or so, maybe. But we could continue by plotting more and more terms, and we would see the same behavior, bouncing to the right and left of 0, but getting closer and closer to 0 as it does. Now the behavior of that last sequence motivates the next definition, which is for the convergence of a sequence. The idea is that as you take more terms in the sequence, if you are approaching some particular number, capital L, and by approaching I mean getting closer and closer to capital L as you take larger and larger values of n, then you have what's called a convergent sequence, and we would say the sequence converges to L. So in the previous example, our sequence was converging to 0. So to make the definition a little bit more precise, instead of saying closer and closer to some number capital L, we really mean that we can get as close as we like to capital L, that there is no limit on how close the terms in the sequence can be made to the number the sequence converges to. So if we take n large enough, we can make the sequence get as close as we like to capital L. If we can do that, we say the sequence converges to L. And if we can't do that for any L, then we say the sequence diverges. So we often use limit notation to indicate the convergence of a sequence. Here we have the limit as n goes to infinity of s sub n is equal to capital L. Sometimes we avoid the limit notation and just use an arrow, Sn arrow L, to represent the same idea. So as we noted, our example that we had graphed has limit equal to 0. In other words, the sequence converges to 0. And we can kind of see that because the numerator here is either 1 or minus 1. It doesn't grow. But the denominator, n, grows without bound. So what we have is a fraction with a numerator that's either 1 or minus 1, and a denominator that's going to infinity, and so that has to approach 0. If we had a sequence defined by, say, the square root of n, well, as n goes to infinity, so does the square root, so that limit would have to also be infinity. Often, instead of writing infinity here, we would say the sequence diverges. Sometimes we would say diverges to infinity. Sometimes we would say does not exist. And then as a last example, the limit of 1 plus 1 over n is going to be equal to 1 because the term 1 over n has a finite numerator and a denominator going to infinity. So as a fraction, it has to go to 0, and so the entire limit ends up being 1. We do have a few different kinds of sequences that we need to be able to recognize. First, we have what are called bounded sequences. The idea here is really just a sequence that doesn't go to infinity or minus infinity. But the definition for bounded is that there's some finite number, capital M, so that every term in the sequence is stuck between minus m and m. It can never get larger than capital M, and the sequence can never get smaller than minus m. So that prevents the sequence from going off to plus or minus infinity. Secondly, we have what are called monotone sequences. So a monotone sequence is one that is either increasing, so that every term in the sequence s sub n plus 1 is at least as big as the term before it, s sub n. In other words, the terms of the sequence in general are increasing, although it is okay for them to stay the same. Similarly, a monotone decreasing sequence is one where the s sub n plus first term is always less than or equal to the term before it. So these would be sequences that are in general decreasing, but again, it's okay if some terms are equal. Finally, we have an important theorem called the monotone convergence theorem. And this theorem is a way of knowing when certain kinds of sequences are going to converge, even if it's not clear to us what they converge to. So the theorem tells us that if you have a sequence and it's bounded and it's also monotone, then you know that the sequence converges to some number, capital L. Now, it doesn't tell you what that number is. It just tells you that somewhere there is a capital L to which the sequence converges. The following examples will give us some practice in figuring out whether a sequence is bounded or monotone, and also whether the sequence converges. First off, we have the reciprocals of the natural numbers. So we're looking at terms like 1 over n. So those are 1, 1/2, 1/3, 1/4, 1/5, and so on. We can plot the terms of the sequence on a number line, where the first term would be 1, the second term would be 1/2, third term would be 1/3, and then 1/4, and then 1/5, and 1/6, and 1/7, and 1/8, and 1/9, 1/10, and so we see that we're getting closer and closer and closer to 0. All right, so this is going to converge, but let's also investigate the boundedness and the monotonicity. So one thing to notice is that all of the terms are stuck between 1 and minus 1. So that indicates that one possible bound for the sequence would be capital M equals 1. So this is a bounded sequence. Now, if we're going to claim that the sequence is bounded, we do have to produce some capital M. It doesn't have to be the best capital M, but we have to at least give one bound within which the sequence lives. So I could have said M is equal to 2, and that would also be a correct bound. Or I could have said M is equal to 10. or m is equal to 16, or a trillion. Those would all be perfectly good capital M's to satisfy the definition of bounded. What I could not have done, though, is set capital M any smaller than 1. So if I had tried m is equal to 0.9, for example, the first term of the sequence, namely 1, would have been outside the bound. So that would not have been okay. As far as whether the sequence is monotone or not, we were moving to the left every time we plotted a point in the sequence. That indicates that the sequence is a monotone decreasing sequence. This is monotone decreasing. Now, because it's both bounded and monotone decreasing, the monotone convergence theorem guarantees that the sequence converges. And in fact, we can see that it converges to 0 just by investigating the limit of 1 over n. Next up, we have the sequence generated by the squares of the natural numbers. So if I wanted to plot this on a number line, first term would be 1, second term would be 4, third term would be 9, and then I'm going to start running out of room. So this sequence increases the whole time, so it is monotone increasing. But it's not bounded. It goes off to infinity. There's no capital M that will contain all points in the sequence. As the sequence is not bounded, it's also not going to converge. So this is an example of one where the limit would be infinity, or we would say it doesn't exist. Next up, we have the alternating sequence of 1s and minus 1s. So let's say this is 0, this is 1, this is minus 1. The sequence is going to bounce between 1 and minus 1. So the first term is minus 1, second term is 1, third term is minus 1, fourth term is 1, fifth term is minus 1, sixth term is 1. So this is an example of a sequence that's not monotone. We're not always increasing or always decreasing. We're bouncing back and forth. So not monotone, but it is bounded. And we have a lot of choice for what we could use for our capital M. Here we may as well use m is equal to 1, because every member of the sequence is stuck between minus 1 and 1. All right, so since we were able to exhibit a capital M, then we now can go ahead and state that the sequence was bounded. As our last example, we have 1 minus n over n. All right, so if we plot the terms of this sequence on a number line, I've got, let's say, 0, minus 1, and 1. The first term is 0. Second term is minus a half. Third term is minus 2/3, and then minus 3/4, minus 4/5, 5/6, 6/7, and so on. So we can see that we have a monotone decreasing sequence because we were always moving to the left, and it is bounded. We could use m equals 2 for this one. Right? So that's bigger than we need, but if I draw in m equals 2 and minus m is negative 2, then we can see that all the terms in the sequence, which are all in here, fall between minus 2 and 2. So it's not the best bound, but it is a bound, and so it works just fine. The fact that we have a monotone decreasing sequence that's also bounded means that by the monotone convergence theorem, we know we have convergence for the sequence. And we can actually see by examining the limit of the sequence or the visualization on the number line that the limit here is going to be -1. So just as a quick discussion of why the monotone convergence theorem is true, let's take a look at how a monotone and bounded sequence must behave. Let's assume here that we have a monotone increasing and bounded sequence. So let's let our sequence S sub n be bounded and monotone increasing. All right, now the fact that it's bounded means there's some capital M, say here, that gives us limits on where the sequence can be, right? All of the terms in my sequence have to be inside that interval minus m to m. The first term in the sequence has to be somewhere on the number line. Let's say it's here, and that's S1. The fact that it is a monotone increasing sequence means S2 has to be somewhere to the right of S1. And S3 has to be somewhere to the right of S2. S4 has to be somewhere to the right of S3. Now in all these cases we could land right on top of the previous term, say right here for S4. But we either have to continue to land right on top of the previous term, or we have to move over a little bit to the right to get the next term in the sequence. So as I continue to do that, I have two choices. I either have to start bunching up so that the terms are all getting closer and closer and closer to some capital L, or I have to move over to the right some more. But the fact that I have this bound here, capital M, means I'm either bunching up to capital L or moving to the right a little bit every time, but I can't keep moving to the right a little bit forever because I would run into the bound capital M. So I either have to bunch up at some earlier point capital L, or eventually I have to bunch up at the point capital M. I can't go past it. So whichever case happens, I've got what the sequence converges to. In this case, I've drawn it as capital L between minus m and capital M. So that's going to do it for sequences. We'll start taking a look at series in the next video. We'll give a very brief definition for a series, and then we'll start working with a particular kind of example called the geometric series. Then in the following video, we'll take a more careful look at the definition for the convergence or divergence of a series and start looking at many different kinds of infinite series. So that will be next time.